Good morning, everyone. This is Celso Batalha, and we are going over solutions of certain key problems, and I would like you to be aware of it. And I will do free fall type of problems, and I will do, and that includes acceleration. I will try to emphasize orientations, vectors, and x and y Cartesian coordinate systems, and I will also play with projectile motion. Okay, take a look at this problem. This is a problem of free fall. So when we work with free fall, get there. So if you are working with free fall, what are the basic issues you should pay attention all the times? First of all, in free fall implies that your object falls with an acceleration that is constant and has a value of 9.8 meters per square second. Okay, this is some given thing. Out of the equations of motion that you have been studying so far, you're going to be using this one that gives you, well, we use I for initial position of your object plus initial velocity versus times plus half of your acceleration t squared. This is an equation that gives you position as a function of time. Okay, if you want to find out the velocity on a given time, this is the equation you use. And in case you do not have time information, you can combine these two equations into this one. V squared is equal to V initial square plus 2 times acceleration times your displacement in y. So this displacement in y is always thought as your final position minus your initial position. Okay, now in this case, and only in this case of free fall, oops, what did I do? In this case of a free fall, that acceleration is given, acceleration points down. It's always your object has a constant force applied on it that pulls it down. Then the acceleration always have this orientation vector pulling down or pointing down, and with this constant value of 9.8 meters per square second. So as I solve problems, here's what I'm gonna do. I will always set my y-axis pointing upward, which means all vectors that happen to be oriented upward, they will receive a positive sign in one of my three equations right here. Okay, now look at this. Your acceleration vector points downward, which is a direction that opposes or is contrary to the one I'm calling positive, meaning your acceleration vector will carry a negative sign. Meaning, when you use your equation of motion, or one of these three equations, what's going to be the different issue? If and only if you set your orientation this way, as I'm doing now, you're going to have a negative sign here times 9.8. Same thing here, minus 9.8. And same thing here, minus 2 times 9.8. Okay? And why why you get yourself this negative sign? It's because the orientation of your acceleration vector. Now we have to look at your initial conditions. So my initial conditions, every time I solve a problem of free fall, will be such that I'm gonna set my base, my ground level, my basic position at the floor. So I'm gonna be sitting right at the floor. So at the floor is where my y-axis is equal 0. Okay? So my y position at the floor is 0. Meaning, if my initial position is on the floor, this y initial is going to be 0 because it's in the floor. Now, if I'm throwing my a projectile, or I'm throwing a ball from the top of a building that has a height, let's say 30 meters, which means if I have a building here, right? I have a building, and from the top of building I just let a ball to fall. Oops. I let the ball to fall like this, right? So my initial position is not going to be 0. My initial position is going to be at the top of the building. If the building has 30 meters, I'm going to write on my y initial 30 meters. Does that make sense? And how about my initial velocity? What is the initial velocity? This is tricky too. So let's say, let me get a better eraser here. Let's say I'm not on a building. I'm not on a building, but I'm on the floor, and I take a rock and I throw upward, like you guys did with the soccer ball. Remember, one of the free fall motion, you took a soccer ball and you throw the soccer ball up in the air in a vertical direction. So when you threw your ball up in the air in a vertical direction, the initial velocity was not 0. It had some value, 1 meter per second, 2 meters per second, I don't remember, but it had some initial velocity, first of all. Second, since the direction in which you're throwing the ball was upward, your velocity vector has a direction, look at this, that is the same as the one you are calling positive. So when you plug this information on your equation, let's say you have an initial velocity that is 2 meters per second, okay? That is the speed of the ball. Now, when you plug that information on your equation, you're going to plug as positive 2 times t. Same thing in your velocity equation. The initial velocity is plus 2 whatever, right? Now, if you had a different situation, you were on the top of the building, so let's bring the building now into consideration. And let me erase this here so I don't it's coming up with a different situation. I'm in the top of the building and I'm gonna throw the ball downward with an initial velocity that is 2 meters per second. The speed is 2 meters per second, but the velocity now is such that I take the ball and I force it down with an initial velocity of 2 meters per second. Look at the vector now. Your velocity vector is directed downward in a direction that opposes that of your positive orientation. So when you plug this information, 2 meters per second, in your equation right here, you're going to plug it in this case that you are throwing it downward, negative 2 times t. So you're going to play with the negative sign. So instead of having this negative sign, positive sign, you are adding, you are including a negative sign. Same thing here, negative sign. Okay, so let's now take a look at this problem. A ball is thrown vertically upward with a speed of 32 meters per second. So what do you have to read here? What is the information you read here? So you have the initial velocity of your ball, 32 meters per second. But velocity implies a number, which is the speed, and implies a direction, vertically upward. So vertically upward means the velocity vector is pointing along the direction we call positive. And we want to find maximum height. How high does it rise? We want to find how long it takes to reach this maximum point, how long it takes to go back to the ground, and what is the velocity when it gets to the ground. Okay? So I took, I already put things in here for you, and here is our three equations, and I step in and I put my negative sign, because again, at any given point, as the ball moves up, at any given point, the acceleration has a value of g and is always pointing in the negative direction and is equal to 9.8 meters per square second. Okay, so here's half acceleration is 4.9. Here's the second equation, v initial minus 9.8, and here is the third equation, or Bernoulli, negative 2 times 9.8 times the change in position. Okay, so let's see how we solve for that. Well, first of all, we want to find the maximum height. So the maximum height is you throw the ball with the initial velocity upward, which means in our equation, our initial velocity must be written as positive 32 meters per second. And the reason is, look at the direction of your velocity vector is the same as that of my y-x, and I will always have my y-x pointing upward, rooted with the tail sticking at ground level where y is equal to 0. Okay, so if I want to find the maximal height, what is the best equation to use? Well, what do I know? I want to find y max. That's good. My initial position, the position where the ball is thrown or the rock is thrown, is y equals 0. So this is 0, right? This is 0. The initial velocity I have 32 meters per second, but I don't know how long it takes the ball or the rock to reach maximum height. I don't know that. So I cannot use this equation of position versus time, because I do not know the maximum height, and I don't know how long it took the rock to go to the top. So which equation is good? Well, let me look at the second equation. The second equation, I could perhaps use it. Why? Well, because when the ball or the rock reach the maximum height, implicit, and this is something you should know, the speed at that point, the velocity at that point is such that is equal to 0 meters per second. Which means when the rock reaches its maximum height, it stops in an instant. it stops and then reverse the velocity, reverse direction, and start falling down. So the ball goes up and it stops at maximum height and then falls down. And what is interesting is counterintuitive. At maximum height, it does have an acceleration that is negative 9.8 meters per square second. And it's a funny situation in which the velocity is zero, but the acceleration is not. So this equation here allow us to determine the time, how long it takes the rock to reach maximum height. But it doesn't give me maximum height. How about the third one? The third one is interesting because if I plug information, the information at maximum height is here, look what I'm gonna get. V final square is 0. Maximum height, velocity is 0. The initial velocity is what? Plus 32 square. Very good. And how about the rest? Del y is equal to what? Final position minus initial position, and then this equation allows me to determine y max. So y max minus 0 is equal to y max, right? Y max minus 0 is y max, so I don't need that. And then I can figure my y max, my maximum height is 32 square divided by 19.6 meters. And then you go to your calculator, or if you want to train your math skills, you just multiply 32 by 32 divided by 9.6. Okay? How about the time for maximum height? Well, since I know the maximum height, I can plug it in here and get the time. I can also use the second equation. Let's use the second equation to find out the maximum time. So if I use the second equation, look at this. Final position or final velocity is equal initial velocity minus 9.8 time that takes to reach maximum height, y max, right? So the t that we want to find is equal to 32 divided by 9.8 seconds. T 32 divided by 9.8 seconds. And then we calculate that part. Good enough? And what is the time to reach the ground? Oh, this is a good thing. So you have several ways of solving for that. To find the time that it takes the rock to find to reach the ground, so from here to there. So how can we solve for that? Well, look at what I'm gonna do. I'm gonna use could I use the second equation? No, because the velocity, if I say, okay, now my initial, just a second, somebody's here. Alright, let's go back. So to find the time that it takes the ball to reach the ground, there are two ways of doing. In fact, there are several ways. Well, I'm thinking about two now. One is this. Okay, let me assume that now my initial situation is up here, right? If my initial situation, I have a situation initial in which the ball is on y max, whatever meters that is. Let me just get a solution so I can use that. 52.2 meters. So the y max we calculated is 52.2 meters, right? and the T max 3.27. It takes 3.27 seconds to go to that point. Okay, so the ball is there, right? Or the rock is there. So what's going to happen now? It's going to start falling. So in this situation, if I think the top part, in fact, let me just do one thing here. These two parts are done, right? We finished that part. And now I have, what is the time? I have a problem, which is this. What is the time to hit the ground? And my initial position now, look at this. My initial position is 52.2 meters, right? What is my initial velocity? My initial velocity, if I consider the top part as my new initial situation, my initial velocity is what? At maximum height, 0 meters per square. Acceleration doesn't change, it is the same. It's always pointing down, it doesn't change. And then I say, well, what can I do? I can say, hey, you know, my final position, when the ball or when the rock hits the ground is what? My final position is y equals 0 meters. So I have final position, I have initial position, I have initial velocity, I have acceleration. Then I can plug all that information in here and get my time. So let's do that. Final position is equal initial position plus initial velocity times t minus 4.9 t squared. Therefore, this is 0. T shall be square root of 52.2 divided by 4.9, whatever the number is in seconds. And if you play your numbers correctly, the time is the same as you had before. So that was what? 3.27 seconds. So the time it takes the rock to go from ground to top part is the same time that it takes the rock to go from the top part down to the ground. It's the same one, as long as there is not air resistance. Remember the exercise we did in the lab? If you have air resistance, the situation is different. With air resistance, as the rock moves up, you have a downward force exerted by air, and your acceleration as a result is going to be bigger than you would have when the ball falls down. When the ball falls down, now the acceleration is going to be less than 9.8, because now you have a upward force provided by air resistance that will diminish the absolute value of your acceleration. And what is the velocity as the ball hits the ground? So how can we solve for that? You can also use the same situation, this same initial condition as we did here. So we say, okay, the top part has initial position given by that. This is my initial velocity, that's my final position, and then I can get, well, final velocity v, I'm going to use my second equation, is equal initial velocity minus 9.8 times the time we just calculated. and then we can get our velocity. Our velocity, as you can see by the sign, will have a negative sign. What does it mean? Well, it means that when in the second segment of this exercise, especially when the ball or the rock is falling down, the velocity vector always pointing downward, which means when you translate that information into numbers, you're going to get yourself a negative sign. If you don't get a negative sign, be attentive, something is wrong. Okay. You could also use Bernoulli for these purposes. You'd have a square root of velocity that would give a couple of values, and you should be able to determine and to select the one that is negative, since your velocity is pointing down. Now, as I mentioned to you, you could decide to do in a different way. Let me show you how. Okay, we want to find the time it took the rock to go from here. I'm sorry, from the top part down here, right? But look at this. We calculate already the time in the part B, the time it took the ball or the rock from here to the maximum height. So let's say if we find a way to calculate how long it took the rock to go from here to the maximum height and back to the floor, so the total time, T total, if I figure that, and if I subtract from the time that I determine in the first segment, then I can have the time of my second segment, which means I have a T1 going up, I have a T2 going down. So if I take the total time and subtract from T1, which is let me see, which is 3.27, I could calculate my T2. So let's do that. So let's say you guys in an exam, the heat of an exam, didn't see the first solution of the one putting the top part as the one with initial conditions. Let's say you didn't see that. But what do you know of your problem? Well, you know that at any given part of the motion, the acceleration is negative 9.8 meters per square second. And you want to find the time. You want to find total time, right? Because you already know the time that it took to go all the way to y max. So look at this. One solution, one possibility is to say, hey, my final position is at y equals 0. For the total time, my initial position is 0, right? It starts from 0. And my final position is also 0, because it goes from the floor and go back to the floor. So if I plug that information in here, what do I got? Y final goes back to the floor is equal y initial, started in the floor, plus initial velocity times t total minus 4.9 t squared. So essentially I have this equation here. 0 is equal 32 t total, I have a total d, minus 4.9 t total square. I can take one of these out, so that 0 is equal 32 minus 4.9 t total. So my t total, the total time, is going to be 32 divided by 4.9. And that is, when you divide 32 by 4.9, you get yourself 6.5. So then you take time for going down, or my T2, is going to be 6.5 minus 3.27, and you're gonna get your 3.27. Of course, there are some little imprecision here in the calculation, but that's the idea. So you got the same result using a different approach. So I took a long time solving this problem, exposing all the possible avenues you have to solve this type of situation. Okay, and then you can always email me or ask me more if you wanted me to do more problems. Let's solve now projectile motion. Projectile motion. Projectile motion. How do we solve projectile motion type of problems? So a projectile motion is one or any motion that has two components. And I like to separate them so you can follow them. One is the so-called component in the horizontal direction, or X component, and the other one is in the Y direction, Y component. The motion in the Y direction is exactly the one I just explained to you in free fall motion. So you have three sets of equations. Y is equal y initial plus v initial t minus 9.8 t squared. The velocity at any given time is initial velocity. This is in y, right? Initial velocity in y, because we are in the y component. Initial velocity in y minus 9.8 t, and the velocity in y at any given time square is equal the initial velocity in y is square minus 19.6 del y. So it's the same three equations you did before, except you are considering only the projections of your initial velocity in y. You are considering only the initial position in y when you set your equations. Now in the x component is one in which acceleration is none. There is no acceleration. The only basically equation you have is x is equal vx times the time. So usually what you're gonna do, you're gonna blend information from here to there. How do you do that? Well, the time is a common parameter in both equations. So the time that it takes the ball, let me show you. So if you have a floor like that, and then you throw a football, the football goes like this, and then falls in there. The time, if you decompose this motion in y and x, here's your x and here's y. So the time it takes the ball to go along this path and hit the floor again, boom, is the same time it would take some observer to follow the ball in the y direction, go up, stopping at maximum height and fall back, as we just studied in free fall motion. Or is the same time it takes some observer that is following the ball kind of a downward in the horizontal component, and like a runner. So somebody throw the football this way, and you have a has to be a very fast runner by the way, that goes along the x direction and catch it right here. Okay, I can't. I don't have two. Can I use two fingers? I don't think I can. Let me see. No, I cannot. This is one finger. No, I can't use two markers. But so Vx is a constant. Vx is constant. It's constant. And Vx is constant. But the velocity in the y component is not, because you have the 9.8 acceleration in the y component. So besides this, what else do you need to know? Well, in this type of motion, usually an initial velocity is going to be given. And let me expand this part over here. So let's say the ball is thrown in such a way, this is the pad is a parabola, but the initial velocity is a vector that is given with an angle in respect to the horizontal. Let's say we have an angle theta right here. So the first thing you do in this problem is to find out what is the value of your Vx and what is the value of Vy, both of them initials. How do you do that? Here is my initial velocity vector. Let's say, so in problems such as this, it is said, oh, a football is thrown with an angle of 30 degrees with respect to the floor, with an initial velocity of 12 meters per second. So 12 meters per second is the magnitude of this initial velocity vector. This is the speed in which the ball leaves the player's hand. Okay. So how do we find the initial velocity in x, which by the way will be constant, and how do we find the initial velocity in y? Now you have to remember your trigonometry. This is your y-axis, this is your x-axis, this is your initial velocity Vy. So the projection is such, this vector is given by the sum of this vector plus this vector. Remember how we add vectors? We take the tail of the second vector, add to the head of first vector, and connect the tail of first vector to the head of the second vector. So here is your Vx initial, and this upward vertical vector is your Vy initial. I just realized I'm switching the indexes. So, and from trigonometry, what did we learn? Well, we learned that Vx initial is equal to V initial cosine of that angle theta, and Vy initial is equal to Vy sine of theta. And you have to play your cards correctly, because you might have a situation that the ball is launched horizontally like this. Let's say, look at the situation. You are at the top of a cliff and you throw a rock parallel to the floor, and the rock is going to fall like that. Right? Here's your initial velocity. What is your initial velocity in x? Well, the initial velocity in x is Vi cosine of 0. Cosine of 0 is 1, right? So your initial velocity in x is Vy. That's it. And what is your V initial velocity in y? Well, is Vi sine of 0, if you want to pick with trigonometry, 0 meters per second. So there is no initial velocity in y in this type of problem. Okay? But if you have a situation, that here's your cliff, right? This is your cliff, this is the ground, and then you have an ocean right there with the water, you know, and you have a little dolphin jumping, and That's a bad dolphin. I don't know how to draw a good one. It's a happy one. So and then you throw your rock not at the dolphin. Come on, don't do these things. You throw a fish. There you go. You throw a fish to feed your dolphin with an angle with respect to horizontal that is theta. What's going to be your different situation now? Well, look at this. As I said, I always set my base at the ground. So this is my y equals 0. Here's my y-axis. And here's my x-axis. This is my x-axis. So this is my y equals 0. So what you do, the first thing you do, you take that information apart before you start doing your problem. Here's your initial velocity Vy. Here's your angle. And let's indicate the projection. Let me put a different color. Can I? I think I can. I have to learn how to do these things. Oh, there you go. So here's my Vx initial, and here's my Vy initial. Now my Vx is given, in this case, my Vx, let me write here. This is my V initial, right? My Vx, in this case, initial, is the same thing, is my Vi cosine theta, the same thing as I had right here, right? Same expression. But how about my Vy initial? Here's the difference. Look at my Vy initial vector is pointing down. Pointing down means the direction of this vector opposes the direction I'm calling positive, meaning it's going to bear a negative sign, minus my initial velocity sine of theta. See the difference? I had a positive number here, and now I have a negative number in there. So let's see how these problems play. In this situation, you have a student at the edge of a cliff, right? And it's throw a stone horizontally with a given velocity. The cliff has a given height, and we want to find all kind of things. Okay, I'm not gonna do the entire problem, but we want to find tons of things. So let's put the information in our board. This is my x-axis, this is my y-axis, and I'm gonna draw a cliff, right? In fact, let me draw the cliff like this. Don't need this part here, and I'm just repeating what I have there, right? I'm just repeating. So my initial velocity is right here. The ball falls like that, whatever falls. My acceleration always points down. That's why I have it as a negative sign, and I have the height, right? I have the height. Okay, so Okay, so this problem kind of summarizes a lot, okay, and it could be more complicated if the initial velocity had an angle like this or like that. So I'm not gonna. I will indicate towards the end what would be different in all your calculation, and I would recommend that you redo that because you might see something like that in your exam. Okay. So first of all, what are the initial conditions? Well, the initial conditions as far as position is concerned, positon, it's almost positron, which is the name of a particle. Position, as far as position is concerned, well, if my base is y equals 0, this is y equals 0 and y grow in that direction, this is positive, and x0 is right here. So the initial position are 2. So I have x and y, right? So remember, we always define an x component and y component. So initial position is such that in y component, y initial is equal 42 meters. Because the initial position is not here. The ball is being thrown from the top of a cliff that has a height of 42 meters. That is the initial position. How about for x? Well, the initial position in x is 0 meters. No problem. How about velocity? Well, the initial velocity in x, is 23 meters per second. Because the initial velocity vector itself is a red in the direction, in the horizontal direction, and will be kept constant all the way. So at any given position in x, x is equal to 23 versus time. Now, what is the initial velocity in y? The initial velocity in y is 0. When you project this vector onto the y direction, it projects none. Okay. What is the equations that helps you to solve this type of problem? This is the only equation you should worry in x. And in y, we have 3, remember? Let me write them here. Y, which means the position in y at any given time, is equal initial position in y, 42, plus initial velocity in y, which is 0, times t, minus 9.8 t squared. And how about the velocity in y at any given time is equal initial velocity minus 9.8 t. So look at this. No matter which time you plug it in here, your velocity vector will be always negative. And that means what? Well, it means that in y direction, the rock or the ball or the fish is always pointing down. And the velocity y at any given point is oriented downward, which is a direction opposite to the one you call positive. Okay. And the third equation is Bernoulli. V squared is equal to 0 squared, which is 0 minus 19.6 del y. Okay. So those are the 3 equations of motion. And if we want to find the time to get to the water, well, the time to, how can we find the time? We can find in this equation here, see that? Because when it hits the water, what do we know? Well, when the ball hits the water, right here, kaboom, and then you have all kind of droplets going up. The y position is 0, because I set that way. So 0 is equal 42 minus 9.8 t squared, and that allows you to determine your time, right? Time is going to be 42 divided by 9.8 square root of this nonsense seconds. Okay, and if we want to find the speed in angle, well, when it gets to this point, the time you calculated here. So and when you divide and take a square root, it's something around 2 seconds. So look at this. I'm going to take this position right here, this dot, and I'm going to write it right here in this little square. So at that point, your velocity vector has two components. It has one component in x, which is always the same, which, you know, is 23 meters per second. It doesn't change. And it has another component in y, which you can determine from this equation, is pointing down. 2 times 2 is the time, times 9.8 is 19.6 meters per second. So how do we add these two vectors? We want to find the magnitude of your velocity vector and the angle phi. So in other words, you have your 23 meters per second like this, and you have your 19.6 meters per second like that, and we want to find the magnitude of this vector. You want to find the speed, which is the magnitude of this vector as it hits the ground. What is the magnitude of your velocity vector? V, and you remember your Pythagoras, is the square root of 23 squared plus 19.6 squared. And that is equal to, and this is equal to about 30 meters per second. Okay, 30 meters per second. And how do we find the angle? How do we find this angle here? Oops. How do we find this angle? Well, this angle phi is an angle whose arc tangent is equal to 19.6 divided by 23, right? And below the horizontal, then you would be done with the problem. Now, if you can organize your thoughts to solve this problem the way we went step by step, you can do any problem with projectile motion, but you have to practice. To complicate matters a little bit, I could ask the same questions, except that now I would say my initial velocity has, which is 23 meters per second, makes an angle of, let's say, 17 degrees with the horizontal. What would be the different thing to do? Well, your initial velocity in x will be different. Your initial velocity in y will be different. Your initial velocity in x, in this case, is 23 cosine 17. And in this case, in my example, the initial velocity in y is positive 23 sine of 17. And if I had flipped this vector, putting downward, now your initial velocity in y would have a negative sign. So try to do these problems by yourself. And if you can't, don't hesitate to email me. Okay?